folks. Welcome to
Vector Calculus.
Alright folks, what's up? Welcome back to the next lecture in Vector Calculus. Today we're taking a look at how to find a line in 3 dimensions. Alright, let's start with 2 dimensions. In 2D, we know that the equation of a line is this: y equals mx plus b. Right, let me take it to you step by step. My m represents the slope of my line, right? The higher the m, the steeper my line. The lower the m, the more shallow my line is. This b over here simply represents where my line hits the y-axis. Alright, so that's pretty simple. Hopefully you know how to plot lines in 2 dimensions, okay? Because in 2 dimensions, all you have is an x and y axis. But in 3 dimensions, hopefully as you know by now, you not only have an x-axis, not only have a y-axis, you also have a third axis, which we call the z-axis, right? So you've got x, you've got y, but you've also got this third axis, z. Now, in 2D, we need one equation to plot a line. How many equations do you think we need to plot a line in 3D? Well, since it's one more dimension, you think it's one more equation. But as a matter of fact, you need 3 equations to describe a line in 3 dimensions, alright? So let me give it to you this way. You need one equation for the x-axis, one equation for the y-axis, and finally, one equation for the z-axis, for the z-coordinate, okay? That's what you need algebraically. You need 3 algebraic equations to define or to describe a line in 3 dimensions. Geometrically, what do you need? Well, in 2 dimensions, we needed 2 points to define a line. In 3 dimensions, we're going to need something a bit more descriptive. We're going to need a point and a vector. What does that mean? That means if you tell me my line passes through this point, that could be thousands of lines. That could be this line, this line, that line. But if you tell me my line passes through this point and is parallel to this vector here, I know that there can only be one line that passes through this point and is parallel to this vector here, right? So passes through this point and parallel to this vector, only one line that can satisfy those conditions. Alright, well, that's all there is to 3-dimensional lines and plotting lines in 3D, right? Just to give you a quick review, algebraically, you need 3 equations to describe a line in 3D, and geometrically, you need a point and a vector to describe a line in 3D. You might be wondering what these letters are, x0, y0, z0. I'll tell you. They're the coordinates of this point, okay? Of the point that our line passes through. And how about A, B, C? Well, A, B, C are simply the components of the vector that our line is parallel to. Let me say that again because it's critically important. What do you need algebraically to describe a line in 3D? Quick, answer the question. You need 3 equations, all of them parametric, all of them defined in terms of t, which you can think of as time, okay? And all of them having x, y, and z, right? Okay. What do you need geometrically to describe a 3-dimensional line? Try to answer that. Well, you need a point and a vector parallel to your line. So if you have a point that your line passes through, you can say something like this. You can bring along a line, and there's hundreds of lines that passes through any given point, right? But there's only one line that passes through this point and is parallel to this vector, right? Only one line. All right, good. And what's the final thing? Final thing you should know is that these are the 3 algebraic equations used to describe a 3-dimensional line. x0, x-coordinate of the point that our line passes through. y0, y-coordinate of the point that our line passes through. z0, z-coordinate of the point that our line passes through. This a value is the x component of the vector that's parallel to our line. This b value is the y component of the vector that's parallel to our line. And this c value is the z component of the vector that's parallel to our line. Okay, good. Now, let's go ahead and take a look at our example. Alright, I'm going to go ahead and write our example on this board, our new studio space, if you will. Let's go ahead and check it out. So we're being asked to find the parametric equation for the line passing, P-A-S-S-I-N-G, passing the point P, positive 2, negative 3, positive 1, and parallel to the vector 1, comma 4, comma negative 3. So let's go ahead and write that down. 1, comma 4, comma negative 3. Okay. So that right there is our problem. Let's go ahead and read it once more. Find the parametric equations for the line passing through this point and parallel to this vector. Okay. First thing you should do. What's the first thing you should do? First thing you should do is get a picture of this, right? Think about this, right? How does it look like? Well, let me go ahead and erase this and help you imagine how our scenario looks like. Okay? So erase all of this. Hopefully you don't need the 2D anymore. Okay? And let's think about how this looks like. What's the point that our line passes through? What's the point? Can you give me the point? Somebody give me the point that our vector passes through. Our line passes through. That's right, it's this point. 2 minus 3, 1. Where is that? Well, this tells you go 2 units in the x direction. So label your axes. This is x, this is y, this is z. Go 2 units in the x, so 1, 2. Go negative 3 units in the y, so that's going to be like hopping 3 units back. And go 1 unit up in the z direction. So here's our point P. Okay? Here's our magical, mystical point. Now, we have our point, but we still need to know what our line looks like, right? What does our line look like? Well, our line has to pass through this point, but remember what I said. There's many lines that pass through any given point. So we need a vector. We need a vector parallel to our line to tell us what direction to go in. And that's this vector. 1, 4, negative 3. Alright, so 1, 4, negative 3, that might look like this. Doesn't have to be on the actual point. That vector might look something like that, and so that helps you kind of orient how your line is going to look like. Previously, your line could have looked like this, that, or that. Now your line can only look like this. And so here's the line that passes through your given point P. Okay, good. Now, how do we find the parametric equations? Well, it's not too bad from here. All you have to do is write down your point P. And what's your point P going to be? Well, it's 2, negative 3, and 1. And from here, you can determine what your x naught, y naught, and z naught is going to be. Your x naught is going to be the x coordinate of your point P. Your y naught is going to be the y coordinate of your point P. And your z naught is going to be the z coordinate of your point P. How about a, b, and c? How do you find those? Well, let me show you. To find a, b, and c, just go ahead and write your vector. 1, 4, negative 3. 1, comma 4, comma negative 3. Well, from here, notice your 1 is going to be the x component of your vector, also known as a. Your 4 is going to be the y component of your vector, also known as b. And finally, your negative 3 is going to be the c component of your vector, also known as c. And so now all we have to do is just plug these numbers in, right? So let's go ahead and do that. We have x is equal to, what's my x naught? Well, you can see that x naught here is 2. Plus, what's my a value? Well, that's 1. And then I just plug on my t. What's y equal to? Well, y is equal to y naught. That's negative 3. Plus bt. And of course, what's bt? Well, that's going to be 4t. And finally, what's z going to be equal to? Well, it's going to equal z naught, which is going to be 1. Plus ct. And what's c? Well, that's negative 3. So I'm just going to write minus 3t. And there you go, ladies and gentlemen. These are the parametric equations of our line, all right? Now, before I leave it to you at that, there's one more thing we might want to cover, and that is symmetric equations, all right? What's the symmetric equation of our line going to be? Well, all that means is you have to solve for this t value, this parameter. So go ahead, solve for this t value. What are you going to get? Well, x minus 2 over 1. Likewise, what will you get when you solve for t in this equation? Y plus 3 over 4. And finally, your final symmetric equation is going to be solving for t in this equation, right? All you're doing is solving for the parameter. Z minus 1 over negative 3. Z minus 1 over negative 3. And that, ladies and gentlemen, is the symmetric equations. These are the parametric equations, and that's all there is to finding three-dimensional lines in 3D space. We'll take you out next time.
Ambition plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.